Okay. So one of the key references that I'm going to use is this Henderson, Perry, and Young text, Principles of Process Engineering. If you have it, great. If you don't, you'll probably be okay, but at some point you might want to get it before the exam because it's got a lot of the tables and things that you'll need for the exam. So it's just a pretty handy reference. ASAB calls it. Okay, so tonight we're going to cover Bernoullis equation and pump applications. And then next we'll go on to fans and some simple drying problems. Well, simple, yeah. I say that, but. So there's principles we're going to look at tonight. Conservation of mass, conservation of energy. And when we're looking at these problems, there's two assumptions that we're making. One is that it's hydrodynamic, so the fluid is moving. So we're only interested in problems where the fluid is moving. You've probably had some statics classes where the water behind a dam, or some of the classical problems where it's sitting still, but we've got it moving. And we're also assuming it's incompressible. So liquids at lower pressures are pretty much incompressible, and gases at low pressures, we're going to assume compressibility. And we do this because it simplifies the problem. We can neglect the changes in fluid density, which we'll see in a minute where that comes in. Okay, so let's start off with conservation of mass. And it's basically that if the rate of flow is constant at any point, and there is no accumulation or depletion of fluid within the system, the principal conservation of mass is withheld. So where mass flow rate is in kilograms per second, so m1 dot, remember the dot over it is telling us that it's a rate. If the dot's missing, then it's just a mass. And this is in a system. So we're looking at a system of pipes or flows. Okay, so for incompressible fluids, the density remains constant, and the equation becomes A1 equals A2 V2 equals the volumetric flow rate. And of course this helps us because if we know 3 of the 4, we can solve for the 4th one. So just to get warmed up, let's do that. I am assuming that you guys are going to work problems with me. Uh-oh. Hang on. There we go. Going the right direction. So as an example, water is flowing in a 15 centimeter inner diameter pipe at a velocity of 0.3 meters per second. Oh yeah, you should be seeing the PowerPoint. So hang on. Why aren't you? Let me share my again and see if we can get this. Are you seeing it now? There we go. Okay, sorry about that. Okay, so we are on the, and you also notice that if on the website there's a handout, which is essentially the slides, but with the answers taken out so that you have to actually work the problem. So if you've seen those, that might help. Then you don't have to copy down the numbers and things. So they're on the ASABE PE exam website. Okay, so we've got water flowing in a 15 centimeter inner diameter pipe at a velocity of 0.3 meters per second. The pipe enlarges to an inside diameter of 30 centimeters. What is the velocity in the larger section? The volumetric flow rate and the mass flow rate. Okay, so we know 3 of the 4, and we know our equation, right? So then we've got the V1 and D2, and we want to solve for V2. But the first thing we have to do is calculate our area, right? Because it's V1 A1 equals V2 A2. So the cross-sectional area is pi d squared over 4. And if we plug in our numbers, we get pi d squared over 4 times the V1, which is 0.3 meters per second. And we divide by the cross-sectional area at the second location. And we've also got to check our units, right? That's something that's going to be important as we go through here, is to check our units and make sure that we've got them consistent, especially when we go to the English units. And you can expect problems in either metric or English on the exam. So if we solve that, then our velocity in the second portion of the pipe is 0.075 meters per second. And the next question was, what is the volumetric flow rate? So think about how we would solve that. We know we want volumetric flow rate, which is Q. And Q is A1V1 or A2V2. And so substituting in our cross-sectional area times our velocity, we get a volumetric rate of 0.0053 meters cubed per second. Okay, now we got to switch to mass flow rate. So we had a volumetric flow rate that was in meters cubed per second, but this is asking for the mass flow rate. So if we think about that, the mass flow rate is our m dot, and really all we need to do is think about what units we have and what units we need. You know, we've got meters cubed per second. We need kilograms per second. So we need to divide by, multiply by kilograms per meter cubed, which sounds an awful lot like density. So the mass flow rate is going to be our volumetric flow rate times the density of the fluid. And in this case, we had water, which is 1,000 kilograms per meter cubed, is the density, or 5.3 kilograms per second as our mass flow rate. Okay, so the density of water is something that if you've got the textbook, you might as well just write that on the inside front cover because you're going to need it a lot. And the other number we're going to need is the density of water in English units. So who knows the density of water in English units? Yes, 62.4 pounds per cubic foot. So that's another one you might as well just write on the inside of your textbook. Okay, so that's a fairly straightforward problem just to get ourselves warmed up. Did anybody have any questions on that? Okay, well, let's go on to Bernoullis Theorem, which is conservation of energy. And Bernoullis Theorem says that since energy is neither created nor destroyed within the fluid system, the total energy of the fluid at one point in the system must equal the total energy at another point, plus any transfers of energy into or out of the system. So one thing that is really important to notice with using Bernoulli's equation is that it applies to one point in the system, and then we pick another point in the system and we write our equation with those 2 points. And then we also in any transfers into or out of the system. So what that means is we can pick our points advantageously to us to help us solve the problem a little easier. So Bernoullis theorem, if you remember, is essentially the potential energy plus the kinetic energy at those 2 points, so point 1 and point 2, plus any transfers into, which would be W, that's the work done to the fluid, or energy transfers out of, which is the friction loss in the system, or F. So we've got H1, which is the elevation at point 1, and P1, which is the pressure, divided by the specific weight of the fluid, plus V1 squared over 2G, which is V is the velocity of the fluid. So there's the kinetic energy, plus W minus F, and then we do the same thing again for the second point in the system. So now the cool thing about Bernoullis equation is that in a lot of the biological and ag engineering problems, we can make some common assumptions. So let's look at a few of those simplifications. Special condition, okay, if the system is open to the atmosphere, then the pressure equals 0 if the reference pressure is atmospheric, so gauge pressure. And either one of the P's or both P's can be 0 depending on the system configuration. So if both points that you choose are open to the atmosphere, then you get to say P1 and P2 are both 0. But it could be that only one of them is. So that's another condition that will help us when we're trying to decide which points to use in Bernoullis equation. Special condition 2. Okay, when one velocity refers to a storage tank and the other refers to a pipe, then the velocity of the fluid in the tank is going to be a lot smaller than the velocity in the pipe, right? Because we've got A1V1 equals A2V2, and if the cross-sectional area of the storage tank is a lot bigger than the cross-sectional area in the pipe, then the velocity in the tank has to be a lot littler than the velocity in the pipe. Okay, in special condition 3, sometimes we can choose points where there's no pump or fan in between the 2 points. So we're not adding energy to the fluid in between the points, so then we know W is 0. We pretty much have to have a fan or a pump in between those points to be adding energy for W to be something greater than 0. Okay, so let's look at an example. So my crude little diagram here, let's assume we have a tank that is, the surface of the water is 125 feet off the ground, and we've got a pipe that's emptying down to this point C. And we're interested in point B, which is 75 feet off the ground, and the outlet is 25 feet off the ground. So if I want to find the energy at B, and I assume the flow is frictionless, then I can use Bernoullis equation and the ability to pick my points strategically to help me find out what the answer is. But let's talk about a few things first. This problem is asking us for the total energy in feet. And we know that energy is not really in units of feet. So why am I asking for it in feet? So the typical units of energy is going to be work, or Newton meters, right? Force times distance. But we can multiply mass times gravity times h, mgh, and if we divide the whole equation through by the mass and gravity, we get h. So basically, we can just normalize and divide through and get units of feet of water, but we can easily convert it back to units of energy. So it's kind of common to see the Bernoulli problems in terms of feet because it's head for the fluid, but that will also be able to convert to units of energy or Newton meters. Okay, so how do we start this problem? The first thing we want to do is remember that it's a conservation of energy problem. So if we go back up and look at the problem, if we knew the energy at A, then that has to be equal to the energy at B, and it has to be equal to the energy at C. So, okay, feet is a measure of pressure. It can be converted to a more traditional pressure unit. Typical units of energy, energy equals work equals Newton meter or foot pound. We can multiply feet or meter by the specific weight of the fluid. We obtain units of pressure. Okay, so how do we start the problem? We think of it as a conservation of energy problem. So we could write the, we can solve for the amount of energy that's at point A, and that will equal the amount of energy at B. So if we look at Bernoulli's equation for point A, really, let's go back to the picture. We can assume that P is 0, right, because it's open to the atmosphere. And the cross-sectional area of that tank is a lot bigger than the cross-sectional area of the pipe, so that the velocity at A is negligible. So then, looking at Bernoulli's equation, we can ignore the pressure and the velocity, and we don't have any W between points A and B, and we're neglecting friction. So then the only thing we have is the height of the fluid that gives us the amount of energy in point A. So the height of the fluid at A is 105 feet, and that equals the total energy at B. That's kind of an example of how we can use the conservation of energy and strategically picking our points when we're solving Bernoulli's equation to get an answer. Okay, so if we want to find the velocity at point C, well, we can set that equal to the velocity at, the energy at A, right? And then we'll have the energy at A, which is 125 feet, is going to be equal to hc vc squared over 2g and the pressure at C, but C is the outlet of the pipe, which is open to the atmosphere, so that pressure is 0. And so then by solving that equation, we're going to get the velocity at and remember that with feet, we're in English units, so our g, our gravitational constant, is going to be 32.2 feet per second squared. Okay, questions on that? Because I'm going to have you try one problem by yourself. Okay, so let's try it yourself. I'd like to leave this problem up here so you can see it, but I'm not sure. Does everybody have Bernoulli's equation written down? Or does anybody need to see the slide that has the Bernoulli equation on it? Well, let me know if you need to see that. Otherwise, I'm going to give you a few minutes to work through this problem. So we've got water. It's pumped at the rate of 3 cubic feet per second through the piping system. If the energy of the water leaving the pump is equivalent to the discharge pressure of 150 psig, to what elevation can the tank be raised? Assume the head loss due to friction is 10 feet. So we don't have it drawn, but there's water coming into the pump, it's pumping, it's adding energy to the water, and when the water is leaving the pump, the total energy is, the pressure energy is 150 pounds per square inch. Okay, so that's going to be the P plus, it's going to be P over the specific weight plus the velocity. So it's an instantaneous kind of measurement. So at that instantaneous moment when the water is leaving the pump, it has no velocity, but it's all pressure, and that pressure is 150 psig. So if you make your first point right at the outlet of the pump, you'll know all the pieces of the Bernoullis equation at that point. And then you have to decide where your other point's going to be. Okay, so try that on your own, and you should be able to, what I want to know is how high can how big is X? That's what I want to know, which is the height that we can raise that tank. So go ahead and type me answers when you come up with them. And you can check your units too, because we've got some conversions that need to happen. How are we doing? So you should have written out the Bernoullis equation, right, for the point that's immediately after the pump. Anybody have a total energy number for that side of the Bernoullis equation? Yes. 346 feet due to the pump alone, correct? And if you didn't get that, then you probably have a units problem. Make sure you write out your units. And then hopefully you set your second point at the top of the reservoir, or the top of the tank, right, where we can assume P is 0, and that velocity is approximately 0. So does anybody have a number yet for X? Yes, 326 feet. So because we set the point 1 on the far side of the pump, our W is 0, right? Because there is no pump between our first point and the second point. We do have a capital F, though, our friction loss, because the problem is telling us we've got a 10-foot head loss due to friction. And then the rest is just adding up the elevation. Anybody not getting 26 that wants to admit it? And any questions on how we got that? Okay, well, seeing none, there's the answer. We are going to go on. Now, in Bernoullis equation, so far, we've either neglected F, the friction loss, in the system, or it's been given to us. But we want to be able to calculate it ourselves. So that's what we're going to do in the next section. We're going to determine loss for piping systems. And step 1 in determining the friction loss is to determine the Reynolds number. So the Reynolds number is dV rho over mu. So the diameter of the pipe times the velocity of the fluid in the pipe times the density divided by dynamic viscosity. So here's where we're going to need to have some tables to get our dynamic viscosity and density of different fluids. Okay, so the first thing we're going to do is practice calculating our Reynolds number. So let's assume we have milk at 20.2 degrees C. It's going to be lifted 3.6 meters through 10 meters of sanitary pipe, which is 2 centimeter inner diameter pipe. Contains 2 type A elbows. Milk in the lower reservoir enters the pipe through a type A entrance at the rate of 0.3 meters cubed per minute. Okay, so the first thing I do is draw myself a diagram. And it looks like we've got a reservoir that's lower, and we've got 2 elbows. So just sketch in 2 bends in the pipe, and then the pipe outlets into another tank. And really, we don't need to know all those details yet, because all we're asked to do right now is to calculate our Reynolds number. So, in order to do that, we need to know the diameter of the pipe, right? Reynolds number is dV rho over the dynamic viscosity. So in Reynolds number, we need to know the velocity of the fluid, but that was not given to us, so we have to calculate that. And we might as well just go ahead and calculate it as squared over 2g also, because we're going to need that in a lot of our calculations. So I usually just do that in the beginning. So our velocity is going to be q divided by a, and before. So our volumetric velocity, our volumetric flow rate, I'm sorry, is 0.3 meters cubed per minute. And of course, minute is a weird unit, so we've got to cut that to seconds. So we have meters cubed per second. And we're going to divide by our cross-sectional area. We know we had a 2 centimeter or a 0.02 meter diameter. So d squared, pi d squared over 4. And if we do those calculations, we get 15.9 meters per second is the velocity of the fluid in the pipe. And then if we just go ahead and calculate v squared over 2g, that answer is 12.9 meters. and the next one should say, one of them is contraction, one of them is expansion. I have this expansion. And then plus the friction loss in the fittings. So we're going to go through and calculate all those different pieces. The friction loss in the pipe, we use Darcy's formula, which is F, that's our friction loss coefficient, times L over D, which is the length of the pipe over the diameter of the pipe. And it doesn't units you use just so they're consistent. L and D are in the same units, so that's dimensionless. And then there's our friend V squared over 2G that we've already calculated. Okay, so really what we need to know there is little f. And in order to find little f, we need to know our relative roughness. And that's going to be a function of pipe material. So relative roughness is a function of the pipe material, and turbulent flow, it is a value needed to use the Moody diagram. So if you have a copy of the Moody diagram, there's one in the book. Let me get that page, but it's really small and you have to have really good eyes to be able to read it. And so I have a bigger version that I've gotten, and those are pretty easy to find, and other textbooks are on the web. So the Moody diagram is on page 23. If you don't have another one for tonight, that'll work. And you notice that along the x-axis, we need to know the Reynolds number. And then along the far right axis, we need the relative roughness. And that's epsilon over D. And if we have those two numbers, then we can find the friction factor. Okay, so let's do an example using Moody's diagram. So if we have a relative roughness of 0.046 millimeter, a pipe diameter of 5 centimeter, and a Reynolds number of 6,312, what is the friction factor? So on my Moody diagram, the x-axis, the Reynolds number, is a logarithmic scale. And so the only problem I've seen students have is getting confused about where 1 times 10 to the 4th is, or 1 times 10 to the 5th. So the first thing to do is orient yourself to your chart, and where you see the 10 to the 4th, that's really like 1 times 10 to the 4th. And then you go to the right and you get 2 times 10 to the 4th, 3, etc. So if we have 17,312, that's 1.7 times 10 to the 4th. So we're going to be right before the 2 times 10 to the 4th. Okay, so you find that value on your x-axis, and then we have to find the relative roughness. But, I mean, so we have to divide, that's the epsilon, I mean, when I see that relative roughness, but epsilon is really only a portion of the relative roughness. So if you have 0.046 millimeters for epsilon, and the pipe diameter is 5 centimeters, we have to calculate the relative roughness, which is, and we have to have those both, of course, in the same units. So if we do that, we get 0.00092, 0.00092. So that's going to be between 0.008 and 0.001 on the far right axis. Okay, so now here's the tricky part. You're going to slide to the left along those heavy dark lines until you intersect with the vertical line from your Reynolds number. But if you come to the curves, you're going to slide up the curves until those two intersect. So in this particular one, you have to slide up the curve a bit until you intersect with 1.7 times 10 to the 4. And then you go straight over to the left to find your friction factor. So this is not trivial. We have to practice this because you don't want to get into the exam and say, now how do I use this thing again? So you're going to find your epsilon over d, and you're going to move to the left until you hit the dark black line, and then slide up that line until it intersects with the Reynolds number. And the answer I got was 0.0285. So if you have a Moody's diagram, check me, see if you get the same number. Of course, that's only part of the answer, because now we have to go back and substitute that into the Darcy's equation in order to get our friction loss for the pipe. The next term is the energy loss due to fittings and sudden contractions. And that is equal to K times V squared over 2G. And that K comes from tables that tell us what coefficient to use based on experimental values. So in the textbook, we've got some tables of K, and that's on page 25. So on page 25, you'll see that there are diagrams for what they mean by entrances. Friction loss due to sudden contraction is table 2.4. And depending on the ratio of the areas, you get different Ks. So we have to sort of know what the fittings and the contractions look like. And then energy loss due to sudden enlargement is V1 minus V2 squared over 2G. But a lot of times, one of those velocities can be approximated as 0 with the V squared over 2G. Okay, so let's go back to our example. We want to calculate F for this milk situation. Okay, so now we really need to draw ourselves a picture. So milk in the lower reservoir. So we've got a reservoir, we've got a pipe coming out of it. It enters the pipe through a type A entrance. And we know that from table 2-3, type A entrance has a K of 0.5. At the rate of 0.3 meters cubed per minute. And we've got two type A elbows. Type A elbows have Ks of 0.5. Okay, and I think that's all we need to be able to solve it. So the first thing we're going to do is find our Reynolds number, which we've done, 154,000. And then we're going to find our friction loss coefficient. I'm looking at that because that's a different number than I just found, but it's pretty close. Oh, that's right, because, yeah, we were doing a different problem before. So, okay, so we've got our epsilon. Oh, how did I get the epsilon? So the epsilon is based on material, and in the textbook there's a table, of course, and that is table 2-2. And 0.046 millimeters is for commercial steel. And the diameter is 0.02 meters, so putting them in common units, we get 0.0023. And our Reynolds number was 1.5 times 10 to the fifth. So now we have to go to Moody's diagram again, and going into the x-axis at 1.5 times 10 to the fifth, and the far right axis at 0.0023, and then we're going to intersect those two lines, and we'll get an F value of 0.026. Okay, and we're going to plug that into our Darcy's equation, or for the friction loss in the pipe. So we've got F is 0.026, and we've got 10 meters of length, 0.02 meters of diameter, and V squared over 2G we've already calculated is 12.9 meters. So F in the pipe is 167.5 meters, but we're not done. Because we've got fittings, expansion, and contraction. So the fittings, well, the contraction, they told us is a type A entrance to the pipe. So going from the tank at the bottom to the pipe, that's our contraction. And we know that's 6.54 meters. And then the fittings, we've got two type A elbows. Each one of them has a K of 0.5. So times V squared over 2G, so that is 12.9 meters. Sudden expansion, the fluid is going to slow down when it is when it's sent into the tank at the top, right? Because area is really large. So we essentially V1 minus V2 squared is equal to V1 squared over 2G, because V2 is really little. Okay, and we add those up, and we get our total friction loss through the system of 199.7 meters. Questions on that? Okay, well, I'm going to have you try it yourself. So let's find the friction loss for milk at 20.2 C. That way you've already got the physical properties that you need for the milk. We've got a volumetric flow rate of 0.075 meters cubed per minute in sanitary tubing. So let's assume that that is commercial steel. I think, let me make sure I made that assumption. Yeah. And with one type A elbow and one type A entrance. So we know those Ks are 0.5. Okay, so the first thing you're going to do is draw yourself a picture. And so we've got a tank with a pipe coming out of it and one type A elbow, and it's discharging into another tank. So it's a pretty simple system. So see if you can tell me what the friction loss in the pipe is going to be. Let me know if you have any questions as you go through there. I think you have everything you need. So step one is you got to figure out what your Reynolds number is. So why don't you calculate your number, and when you get it, type it up there. Let me make sure that you're on the right path there. So you should by now have the velocity in the pipe, right? Because you need that in order to find the Reynolds number. So what velocities do you have? Or is everybody asleep? Taking a break? How about cross-sectional area, which you need to find the velocity? Yes, 0.99 or 1 meter per second for V. Yep. And if you didn't get that, check your units. I sound like a broken record, but we had a volumetric in meters cubed per minute, so you had to convert that into meters cubed per second. Okay, so then the next thing is calculating your Reynolds number using a velocity of 1 meter per second. Yes, 19,343. Great, that's your Reynolds number. So then you're going to want to calculate your friction loss in your pipe. And we're going to assume an epsilon of 0.046 meters. anybody have their little f yet? Loss coefficient? .029. Yep. Okay, so now you're ready to do your friction loss in your pipe. So what are we getting for the friction loss in the pipe? Everyone has gone quiet. So the friction loss in the pipe, we've got our friction loss coefficient, so 0.029 times L over D, or 20 meters divided by 0.04 meters, times V squared over 2G, which is a little number. Let's see. .05 meters squared per second squared. Yeah, friction loss due to flow in the pipe is 0.73 meters. Yep. So you've got such a small v squared over g that we don't get a whole lot of contribution from the expansion, the contraction, or the elbow. Okay, so there's a lot of parts to these problems, and likely the exam, since it's multiple choice, is not going to ask you to do the whole problem all the way straight through, but they'll give you pieces. They'll give you pieces of information. So you need to know how to do the problem all the way straight through so that you can figure out where they're jumping in, you know, where you can take the information they gave you and come up with the answer that they're asking for. So I don't know, I think the best thing to do is study the whole problem like this, and then just think about, well, what would you do if they gave you the Reynolds number, or if they, I don't know, gave you the friction loss in the pipe, and just ask you to find total F. Okay, so let's go on. Now, we're doing all these things because we want to be able to size pumps. And next time we'll also do fans, but tonight we're going to look at pumps. So in the Bernoullis equation, the pump is represented by W, right? It's the work that the pump adds to the system. So we can find out how much work we need to add to the system by just solving the Bernoullis equation for W. And then that'll be the amount of energy that we need to add with the pump. So W is used to compute the size of pump needed. Power output of a pump is calculated by P sub 0, so P output, equals WQ rho G. So W is the work from the pump in feet or meters. Q is the volumetric flow rate, cubic feet per second or meter cube per second. And then we've got density and we've got gravity. So the other thing to remember is where we're at in the system so that you're giving the right number for whatever the question asks. So the power output is going to be the power delivered to the fluid, and sometimes that's referred to as the hydraulic power. So remember in that sample problem we worked where we had the pressure of that was exerted on the fluid right at the entrance, right at the exit of the pump. That's the number P naught is. And then we have P in, which is the power in, and that's the power out divided by the pump efficiency. And this is sometimes referred to as the brake horsepower. Now remember that these P's represent power and not pressure. That can get a little confusing. So to calculate power out, what we know W, rho, and G, and we need a Q. But with these pump systems, the flow rate, the Q, is variable because it depends on the back pressure. So it depends on the system, what system we're on, right? Because the back pressure is really like the friction loss in the system. So we have to find the intersection of the system characteristic curve and the pump curve if we want to know what the flow rate's going to be with that pump on that system. So the system characteristic curves is calculated by solving the Bernoullis theorem or the Bernoullis equation for many different Q's and solving for W. And this curve tells us the power needed to be supplied to move the fluid at that Q through that system. And here's an example of a system characteristic curve. So along the x-axis we have a range of volumetric flow rates, and on the y-axis we have their corresponding W's, or total head. So if you think about it, it's going to take a lot more work to push more volumetric flow rate through a system than it would if you're pushing just a little bit of the volumetric flow rate through, and most of the time it's not a linear relationship, it's curvilinear. And it's so system dependent that we're going to calculate it for each system. Okay, and then we have the pump performance curves. And this is all about the pump. And this is typically given by the manufacturer. And it plots the total head against Q, the volumetric discharge rate. And the caveat here is that these curves are good for only one speed and one impeller diameter for the pump. And what we're going to do later after we finish this section is find out how we can sort of modify these pump performance curves if we wanted to change speeds of the pump or if we wanted to change diameters. We've got some pump laws that we can use to get a good approximation of what would happen to our pump performance curves. Okay, so here's a typical pump performance curve. And along the x-axis, again, we have volumetric flow rate. And on the y-axis, we have a couple different things. We have W, or the head, in meters. And we also have P, or power, in watts. And then we have several different curves on the pump performance curve. We have total head, we have power, and we have efficiency. Those are typically what you see on the pump performance curves. And you'll notice down in the bottom left-hand corner that this says this pump performance curve is good for N equal 1760 RPM. So that's the pump speed. And diameter of the impeller is 15 centimeters. Okay? So the pump operating point is found by the intersection of the pump performance curve and the system characteristic curve. So if we're going to take a pump and put it on that system, we look at the intersection of the curves and we'll find out what Q we'll get, what flow rate we'll get from that system and what head it will be operating at. Okay, so looking at this graph, we've got a system curve and we've got the pump characteristic curve, no, the system characteristic curve and the pump curve, pump performance curve intersection, right? So the question is, what volumetric flow rate will this pump discharge on this system? So you're going to go to the intersection of the total head and the system, and it'll be about 0.005 meters cubed per second will be the discharge. The only tricky thing on these is to remember that we need the total head from the pump performance curves, because that's what the system curve tells us, right? We know that W, which is what we're plotting for the system characteristic curve, is in meters, and it represents the head, the W, that we need from the pump. Performance of centrifugal pumps is, while pumping water, is used as a standard for comparing pumps. So if no fluid is given in the problem, you can assume it's water, because that's the reference fluid. Okay, and then if we want to compare pumps at any other speed than that at which the tests were conducted, you know, to get the pump performance curves, or to compare performance curves for geometrically similar pumps, so different diameters, we're going to use the affinity laws. Okay, so the pump affinity laws are given to us in a couple different places in the textbook. So they're given to us on page 106. And they basically, if you know one set of properties, so for the original pump, and then you have the second set of properties for the situation that you want to create, you can solve for the missing variable. So let's say you knew Q1, and you know N1, the speed and the diameter, and then you also know the speed at which you want to run the pump and the diameter at which you want to change the pump, then you can calculate Q2, the new volumetric flow rate. Now, the pump affinity laws that are on page 106 are only for changing one parameter at a time, one property at a time. So you could change the diameter, but a lot of times we want to change more than one. Okay, but let's do this example. Size of pump that is geometrically similar to the pump given in the performance curve below, which I don't see, for the same system. Find D and N to achieve a volumetric flow rate of 0.005 meters cubed per second against a head of 19.8 meters. Okay, so there's the pump performance curve. And what we really want to do is to map the new pump on the same system curve. So the first thing we're going to do is find the operating point of the original pump on this system. So you'll have to plot your system characteristic curve onto your pump curve. Okay, so then we can read off this all the parameters that we need. So in this particular case, we read off that for the first situation, we have a Q of 0.01 meters cubed per second and a power of 882 watts at speed of 1760 and a diameter of 17.8 centimeters. So I like to set up these tables when I'm using the pump affinity laws so that I don't get confused. So for the first one, N is 1760 and diameter of impeller is 17.8 centimeters. And the original volumetric flow rate is 0.01 meters cubed per second. And the problem gave us Q2 equal 0.005 meters cubed per second at a head of 19.8 meters. So that's what we know, and we're trying to find actually, I forgot. What did he ask us for? Oh, the diameter of the impeller and the speed to achieve the new situation. Okay. So we want N2. So how do we convert the power to head? You remember from the first slide in this section, the power out is WQ rho G. So if we have W, that's going to equal the power divided by the flow rate, the density, and the gravitational constant. So we know the power out is 882.9 Newton meter per second because we read that off our pump curves. And we know Q because that was the intersection of our pump performance curve and our system character curve. And we know, of course, we know the density of water, we know the gravitational constant. So solving for that, we get the head is 9 meters. meters. So that's and then for next time, if you can make sure you have a psychrometric chart, both English and metric, that would be handy. One that you can read, because the one in the textbook's really hard to read. I'll also try to put one up on the site too, so you can have one if you can't find one. We have to remember how to read those. You're welcome. And next time, the next section is a little bit longer, so we'll probably be here till 9 o'clock next time, but maybe not since we're a smaller group. But thanks, everybody.